Section 6.2, linear programming problems. So in this section, what we're going to do is learn how to set up the linear programming model. And then in section 6.3 and in 6.4, we will actually be solving them. So what is a linear programming problem? Well, a linear programming problem consists of a linear objective function. We'll look at what that entails by way of example in just a little bit. Anyway, it consists of this objective function to be maximized or minimized subject to certain constraints in the form of linear equations or inequalities. This is what we were just talking about in section 6.1, looking at a system of linear inequalities. So that certainly is going to be a part of section 6.2, as well as other sections moving forward as we wrap up the material for the finite mathematics course. So the objective function, this again is a function that's going to be optimized, okay? So these are two different examples of that. Profit, you'd want to maximize. Cost, you'd probably want to minimize. So we'll take a look at these, again, by way of example as we finish up the material we need to look at in chapter 6. So the last bullet point here I have is, if we're looking at material in section 6.3, we still need to remember all the guidelines and follow the procedure from section 6.1 in order to successfully graph our solution region. All right, so we only have this section and then section 6.3 and 6.4 to go to finish out the semester. So let's go ahead and take a look at two examples in section 6.2, and then again, we'll solve these in section 6.3 and in 6.4. There's two different methods we're going to look at in section 6.3 and in 6.4 in terms of solving a linear programming problem. All right, let's take a look at our first example. So we're not going to actually solve these linear programming problems yet, just like I stated a little bit ago. All we're going to do is formulate as a linear programming problem. So I would highly recommend you look at the notes that I've attached here. So it's going to make it easier for you to follow along as I set up this particular model. Okay, so I'm going to underline some key pieces of information here in order to ultimately construct my linear programming model. So we're looking at producing two models of fireplace grates. So we have a model A and a model B. We know that to produce each model A requires what? 3 pounds of cast iron, 6 minutes of labor. To produce each model B requires 4 pounds of cast iron, 3 minutes of labor. And then the profit here for each model A grate is $2, and the profit for each model B grate is $1.50. Okay, we also know what? We know if there are 1,000 pounds of cast iron, and we also know there are 20 hours of labor that are available for the production of these grates. All right, so let's use this information to ultimately construct our linear programming model. So what we're going to do is first define our unknowns, define our variables. So X is going to be the number of model A grates, and Y is going to be the number of model B grates. All right, so what I would recommend you do at this point is construct a table of some sort to help you keep your information organized. So what I'm going to do is that right now, so I'm going to have what? I'm going to have a column heading A for A grates, and column heading B for fireplace model B grates. And in this final column, I'm going to label as the max available. And this is going to be referring to the materials we have to actually produce these particular types of fireplace grates. So what material are we talking about? Well, we're talking about iron. And iron is going to be with respect to what units? Pounds. And then we have, well, labor, right? You do not have an unlimited amount of labor. You have a limited amount of labor, and we're going to call it minutes available to construct these particular model grates. All right, so what do we know from the question? Again, that should be in front of you. Look at what it says for Model A. Model A says what? 3 pounds of cast iron, 6 minutes of labor. So we're going to put a 3 here and a 6 there. Model B requires 4 pounds of cast iron, 3 minutes of labor. Okay? And then it goes on to say later on in the problem, 1,000 pounds of cast iron and 20 hours of labor. So 1,000 pounds of cast iron, but then 20 labor hours. Well, it has to be in terms of minutes. So that's going to be 20 times 60, or 120 minutes. Now that we have our data, let's go ahead and see how we can convert this into our linear programming model. So at this point, I'm going to recognize that every row here is going to represent a linear inequality. So the first row is going to represent this, 3x, because x is the number of Model A grates. We're looking at, column x here. So 3x, and then what? Plus 4y, y being the number of Model B grates coming from column B. And then that's going to be less than or equal to 1,000, because this is the max we have available. We don't have to use all of it, but we only have this much available. So you can use up to 1,000 pounds of iron. Moving to the second row here in this, what is really just a matrix. You'd get 6x plus 3y is less than or equal to 1,200. The other restriction we have to make sure we include would be these two. X has to be greater than or equal to 0, and y must also be greater than or equal to 0, because we're talking about a real life situation here, which means we are only looking at positive x and positive y values. So graphically, this system would only be occurring in quadrant number 1. All right, the last thing we have to do is come up with our objective function. All right, so in this case, our objective function is based on profit. Okay, so it says again, the profit for each Model A grate is $2. The profit for each Model B grate is $1.50. We're trying to figure out how many of each model should we produce per day to maximize Kane's profits. Again, we're not actually going to be solving these today, but we should certainly be able to come up with our model. So we are going to be maximizing what? Well, here is what we're going to be maximizing. It's going to be profit. So write down P for profit. And then what is that going to be equal to? P is going to be equal to what? 2x, because it was $2 per Model A grate, plus 1.5, because we were told we'd be making $1.50 for each Model B grate. So this is the linear programming model that we would end up with based on the given information in question number 1. And again, we will actually be solving these types of problems in section 6.3, and then we'll also be solving them in section 6.4. Let's look at example number 2.